Hello, welcome to my channel. In this video, we are going to be taking a look at damped oscillations. In our previous video, we looked at simple harmonic motion. In that video, we noticed that simple harmonic motion, when a body undergoes simple harmonic motion, the body oscillates to and fro for a very long time without coming to rest. But in a real life situation, we know that when a body oscillates, at a point in time, it will come to rest. And the reason why it comes to rest is because of damping. And we want to take a look at what causes damping and solve equations governing damped oscillations. So we'll start with this diagram. We have a block that is connected to a spring. Now, this spring, when it is unstretched or when it is not compressed, then its original position is x equal to 0. So when you apply a force that tends towards this direction, we notice that we'll have, just like in our previous video, we'll have what we call the restoring force, which we tend to want to bring it backward. And because of damping is involved, there is what we call the damping force, which will also oppose this particular one. The damping force could be as a result of friction or other form of forces that can be as a result of the design of this spring. So the first one is the restoring force, which is giving us F equal to kx, where k is our force constant, right, multiplied by the position x, which is the extension. Then we also have the damping force, which is giving us F equal to bv. Our v here is the velocity. Our b here is the damping constant. So our force here depends on the velocity. So the higher the velocity, the higher this force, or which is called the damping force. Now we can see that the sum from Newton's law, the sum of all the forces, when this force is no longer there, because you need this force to stretch, and when you now release it, these two forces will tend to pull it backward. And when this block goes backward, as it is coming forward, right, these two forces will definitely act against the motion. So the sum of all these forces, right, is equal to F. We have it as from Newton's law. We can see that our minus kx minus bv, because they oppose the motion of this particular block. Now, our F here becomes ma, so we'll replace with ma, which is equal to minus kx minus bv. We already said that our v is velocity. So if we rearrange this this equation, we have ma plus bv plus kx equal to 0. And if we put it in a differential form, where our a here is the same thing as d squared x dt squared, our v is dx dt, we have something of this form, right? Then we can also rewrite this equation as this in a short form, where our x dot dot represent d squared x dt squared. Dx dt is x dot, right? It's a shorter form of writing this expression. So if we solve this particular problem, we have a special solution. And if you check our previous video, which is titled Mathematics for Scientists and Engineers, we solved an equation of this form. So we don't have to solve it here. So the solution to this differential equation is giving us x equal to a naught exponential minus b all over 2mt cos w prime t plus phi. Now, if you take a look at this equation compared to the solution to our previous system, which is simple harmonic motion, this is the only part that is not there, this part. So, but for damped oscillation, this one is now introduced, right? So let's take a look at the effect of this particular expression in this equation. So we have a diagram of this form, right? Where we have, if this part is not there, we have only a naught cos wt. It means that's a normal simple harmonic motion. And this is a diagram, the blue curve. We have it this way. So we see that it will continue to oscillate at a constant amplitude. It will continue to oscillate. But when we introduce this particular equation, this particular expression into this equation, and we plot against x against t, then we now have this black curve. We can see that the amplitude gradually reduces. The amplitude gradually reduces until it becomes, until it vanishes. So that's it. So the exponential term, if we plot only the exponential term alone, it's an exponential curve which decreases with time towards, as the time increases towards infinity, this particular part decreases towards zero. Okay, so that's the effect of damping on the oscillation of the system. We can see that the amplitude decreases with time. And this is a real life situation. Unlike this one, which is an ideal situation, which is simple harmonic motion, this one is a damped oscillation. Okay, so let's see what we can do. Our W prime here is no longer the square root of K all over M that we used to know it as. But our W prime here is now the new expression called square root of K all over M minus B squared all over 4M squared. Right? So where our K all over M here, if we take the square root, is usually termed the natural angular frequency, while this one is as a result of the damping. Okay, so we have W naught squared equal to K all over M and W squared equal to B all over M, right? So if we substitute this one into this, we have W prime equal to W naught, which is the natural angular frequency. This one is just our normal angular frequency for the system, damped angular frequency. Okay, so at this point, we can say that when B is very large, that is, this B is very large. Take note, as B increases, a point will come where this one will be exactly equal to this. And when it is exactly equal to this, everything inside there will become zero as you continue to increase this value, because this value naturally is smaller than this. But when you increase this value, it will continue to grow to a point where it will be equal to this expression. And at that point, K all over M minus B squared all over 4M squared will be equal to 0. So we have W prime will be equal to 0 at that point, right? And as a result, we have Km equal to B squared all over 4M. So if we make B the Soviet formula, we can have several scenarios. And the first point is where B equal to 2 square root of Km. If you make B the Soviet formula, you get this. Now, when B is equal to 2 square root of Km, we call that particular scenario or that situation critical damping. So we call it critical damping. That means the system returns to equilibrium without oscillating when you displaced it, when it is displaced. The second scenario is when B is greater than this. So we have B is greater than 2 square root of Km. That is, this one here is greater than this particular one, right? You notice that when this is greater than this, we will get a negative value, and the square root of this will give us a complex. So in that situation, we call it over damping. So in that case, the system returns to equilibrium without oscillating more slowly than critical damping when displaced. So it will return to equilibrium position more slowly compared to this one. So we call it over damping. Now the next scenario is when B is less than 2 km. That is, this one is less than this. In that scenario, we call it under damping. And under damping, this system will oscillate with a steadily increasing amplitude. I hope that's okay. And we can look at the diagram that describes these three situations. So we have the first case, we have this diagram. So if we look at this red line, it is when B is greater than 2 km. So this one is called over damping. So you can see it does not oscillate, but it goes to the equilibrium position. This is equilibrium position slowly. Compared to this blue line, which is equal to B equal to 2K, that's a critical damping. We can see that it goes to equilibrium and it also does not oscillate. Then finally, we have B less than 2 square root of Km. In that case, we call it under damping. We can see it oscillates, but it gradually dies down. Okay, so that's it for critical damping, under damping, and So hopefully in our next video, we'll definitely solve problems under that. So, but it's important for us to take a look at the amplitude. A is equal to this part. The cause part is the part responsible for this oscillation, that cause part. So for damping, the new amplitude is now A naught exponential, this part. So it's important for us to connect the amplitude, let's say from here to here, with this to this, with this to this. We want to see how the amplitude for the different periods are related. So we can say that A naught is equal to A naught exponential minus B all over 2m when t is 0. That's from here to here when t is 0. These are t. When t is 0, from here to here, we call it our amplitude A naught. Then A1 is from here to here when our amplitude is 2 pi, right? Then we have the next one. If we take the ratio, we have exponential this all over this part, and which simplifies as A naught all over A1 equal to exponential 2b pi all over m. And we can see that this ratio A naught all over A1 equal to this is also equal to A1 all over A2, and likewise A2 all over A3. So that's it. I hope this helps. Please like, share, and follow for more. Thank you.